Picture a chalkboard. Not the clean green kind you might remember from school, but the old slate kind, dark, heavy, covered in a fine white dust that clings to fingers and smudges across sleeves. It is 1997, and this particular chalkboard stands in a lecture hall at the University of California, Santa Barbara, where a physicist named Leonard Susskind has just written something that will take 2 decades to prove. The symbols on the board mean almost nothing to anyone passing in the hallway. Greek letters, integrals, a sketch of what looks like a cylinder with wavy lines inside it. But to the 30 or so people sitting in that room, these marks are making a claim so outrageous that some of them will spend the next 20 years trying to tear it down. The claim is this: everything you see, everything you touch, every atom in your body and every star in the sky is a kind of illusion. Not a lie, exactly. Not a simulation in the science fiction sense. Something stranger. The universe, Susskind is suggesting, might be a hologram, a 3-dimensional projection cast from information written on a distant 2-dimensional surface. You feel depth, you feel weight, you feel the solidity of the chair beneath you, but all of it, every cubic inch of space you have ever moved through, might be encoded on a flat sheet at the edge of reality, the way a credit card hologram stores a 3-dimensional image on a thin foil strip. If that sounds impossible, you are not alone. One man in particular thought it was worse than impossible. He thought it was dangerous. His name was Stephen Hawking, and he was about to go to war. Consider tapping that like and subscribe button if these slow journeys help you think or help you drift. A single tap is always appreciated. Now let us begin. To understand why 2 of the greatest minds in physics would spend 20 years fighting over whether the universe is a hologram, you first have to understand what they were fighting about. And to understand that, you have to go somewhere strange, somewhere dark, somewhere so extreme that the ordinary rules of physics begin to tear themselves apart. You have to go to a black hole, not the Hollywood version, not the swirling disk of fire and the pull of doom. The real thing is quieter than that and stranger. A black hole is a region of space where gravity is won so completely that nothing, not light, not information, not even time as you understand it, can escape. Cross the boundary, and you are gone. Not dead exactly, not yet, but unreachable, disconnected from the rest of the universe in a way that has no analogy in ordinary experience. That boundary has a name. It is called the event horizon. And in the 1970s, a young physicist in a wheelchair realized something about it that would haunt science for the next 50 years. Stephen Hawking was 32 years old in 1974. He had already been diagnosed with motor neuron disease. He had already been given 2 years to live. He had already outlived that prediction by a decade, and he would outlive it by 4 more. But in 1974, he was still relatively unknown outside his field. A brilliant theorist, yes, but not yet the cultural icon he would become. That changed because of a single calculation. Hawking was trying to understand what happens at the edge of a black hole. Classical physics said nothing could escape, but Hawking was not thinking classically. He was thinking quantum mechanically, and when he applied the strange rules of quantum mechanics to the event horizon, he discovered something that should not have been possible. Black holes glow, not brightly, not visibly. The radiation is so faint that no telescope in existence could ever detect it. But it is there, a slow, steady trickle of particles leaking out from the event horizon, carrying energy away from the black hole and into the universe beyond. This radiation now bears his name, Hawking radiation, and its discovery made Hawking famous, but it also created a problem so severe that it nearly broke physics. Here is the problem as simply as it can be stated. Hawking radiation has no memory. When a black hole radiates, it loses mass, slowly, unimaginably slowly. For the black holes we observe, a stellar mass black hole would take longer than the current age of the universe to evaporate even slightly. But eventually, given enough time, any black hole will shrink, and shrink, and shrink, until one day it vanishes entirely. Now think about what went into that black hole during its lifetime. Stars, planets, gas clouds, perhaps spacecraft, perhaps civilizations, perhaps libraries full of books and minds full of memories and every piece of information that ever defined those things as distinct from empty space. All of that fell in, all of that was swallowed, and when the black hole finally evaporates, where does it go? Hawking's answer in 1974 was devastating. It goes nowhere. The radiation that escapes is thermal, random. It carries no pattern, no structure, no imprint of what fell in. A black hole that swallowed a Shakespeare folio and a black hole that swallowed the same mass of random gas would at the end produce the exact same radiation. The information would be erased, permanently, irretrievably. This is called the black hole information paradox, and it is not a small problem. In quantum mechanics, information is sacred. It can be scrambled, it can be hidden, it can be spread across so many particles that no conceivable computer could ever reassemble it. But it cannot be destroyed. This is a law, not a suggestion, not a guideline, a law. The mathematics of quantum mechanics simply does not allow information to vanish. And yet here was Stephen Hawking, one of the most respected physicists alive, proving that black holes must destroy information, that the universe must have a mechanism for permanent irreversible erasure. Something had to give. Let the weight of that settle for a moment. Two pillars of physics, general relativity, which describes black holes, and quantum mechanics, which describes everything else, were in direct contradiction. One of them had to be wrong, or both of them had to be incomplete in some way that no one yet understood. Hawking was confident he knew which one would bend. Quantum mechanics, he argued, was an approximation, a useful tool for small scales. But at the extremes, at the edge of a black hole, where gravity warped space beyond recognition, the neat rules of quantum theory simply broke down. Information could be lost because black holes were not really quantum objects at all. They were something else, something that played by different rules. Not everyone agreed. On the other side of the country, in a cramped office at Stanford University, Leonard Susskind read Hawking's papers and felt something between admiration and alarm. Susskind was a different kind of physicist than Hawking. Where Hawking was elegant, precise, almost classical in his approach, Susskind was restless and intuitive. He had started his career as a plumber's son in the South Bronx, working his way through City College of New York before stumbling into theoretical physics almost by accident. He had a street fighter's instinct for which arguments were solid and which ones were bluffs, and when he read Hawking's claim about information loss, every instinct he had said the same thing. This cannot be right. But saying it could not be right and proving it could not be right were very different things. Hawking's mathematics was impeccable. His reasoning was clear. If you accepted his premises, his conclusion followed inevitably. Susskind would have to attack the premises themselves. The question was, which premise was wrong? Here is where the story takes a turn that no one expected. In the early 1990s, Susskind was not thinking about black holes. He was thinking about strings. String theory had emerged in the 1980s as a candidate for the long-sought theory of everything, a single mathematical framework that could describe all the forces of nature, from gravity to electromagnetism to the nuclear forces that hold atoms together. The central idea was deceptively simple. What if the fundamental building blocks of reality were not point-like particles, but tiny vibrating strings? Different vibrations would correspond to different particles, the way different vibrations of a guitar string correspond to different notes. It was elegant, it was ambitious, and it was at the time almost impossible to test. But string theory had one property that Susskind could not stop thinking about. It had boundaries. In certain versions of string theory, the universe was not infinite in all directions. It had edges, walls, surfaces where the mathematics behaved differently than it did in the bulk of space. And when Susskind stared at those surfaces long enough, he began to see something strange. The information content of the surface seemed to match the information content of the space inside it. This was counterintuitive in the extreme. Imagine a room. Now imagine painting every fact about what is inside that room. The positions of the furniture, the colours of the walls, the exact arrangement of every atom, onto the surface of the room's walls. You would expect to need more information on the inside than could possibly fit on the outside. The inside is three-dimensional. The outside is two-dimensional. There is simply more room inside. But string theory was suggesting otherwise. The mathematics seemed to indicate that everything inside a region of space could be fully described by information on its boundary. As if the interior were not the real thing at all. As if the boundary was somehow primary, and the interior were a kind of projection. A hologram. Susskind called this idea the holographic principle, and he realized almost immediately that it might solve Hawking's paradox. Think about it this way. If information is not really located in the interior of space, if it is actually encoded on distant boundaries, then a black hole cannot truly destroy information. The information might fall past the event horizon. It might become inaccessible to anyone outside, but it would still be there, encoded on the horizon itself, waiting to be released as the black hole evaporated. No information loss, no violation of quantum mechanics, just a radical new way of thinking about where information lives. But there was a problem. Hawking did not believe it. To understand why Hawking resisted, you have to understand how different his picture of reality was from Susskind's. Hawking was a relativist. He thought in terms of curved space-time, in terms of geodesics and light cones, and the smooth fabric of the cosmos stretching and bending under the influence of mass and energy. For him, the interior of a black hole was real in the most fundamental sense. It was a region of space-time, no different in principle from the space-time outside, just disconnected from it. Susskind was proposing something that sounded to a relativist like madness. He was saying the interior might not be real at all, that what we experience as depth, as volume, as the three-dimensional stage on which physics plays out, might be a kind of elaborate reconstruction from a two-dimensional truth. For Hawking, this was not just wrong, it was philosophically unacceptable. It smelled of the kind of thinking that substituted mathematical cleverness for physical insight. He had spent his career understanding what black holes really were, what they looked like from the inside, what an astronaut falling in would experience, how time and space themselves twisted near the singularity. And now Susskind was suggesting that all of this might be, in some sense, a mirage. The battle lines were drawn. On one side, Hawking, arguing that information was truly lost, that quantum mechanics was incomplete, that black holes were the places where the rules broke down. On the other side, Susskind, arguing that information was never lost, that quantum mechanics was sacred, that our entire picture of space and reality would have to be rebuilt before we allowed a single bit of information to be erased. They were not arguing about angels on the head of a pin. They were arguing about the nature of reality itself, about whether the universe had a memory, about whether anything at all could ever truly be forgotten. And neither one was willing to give an inch. The years that followed looked, from the outside, like an ordinary scientific debate. Papers were published, conferences were held, ideas were proposed, criticized, revised, abandoned, revived. The black hole information paradox became one of the central problems of theoretical physics, attracting brilliant minds from around the world. But beneath the surface, something more personal was happening. Hawking and Susskind had known each other for years. They had attended the same conferences, collaborated on adjacent problems, respected each other's work. But as the debate over information loss hardened into opposing camps, respect began to shade into something more combative. Susskind would later describe the conflict in terms that surprised people who knew only Hawking's public image. The gentle genius in the wheelchair, the author of A Brief History of Time, the voice of wonder synthesized through a computer. Stephen was a fighter, Susskind wrote. He didn't just disagree with you, he wanted to crush you. And Hawking did not limit his attacks to academic papers. At conferences, he would publicly mock the holographic principle. He called it wishful thinking. He called it mathematically naive. He suggested, in terms that stung precisely because they came from Stephen Hawking, that Susskind and his allies were letting their attachment to quantum mechanics cloud their judgment, that they were so desperate to save information that they were willing to believe absurdities. Susskind pushed back just as hard. He accused Hawking of abandoning the very principles that had made him great, of retreating into a comfortable picture of black holes rather than following the mathematics wherever it led. The holographic principle was not wishful thinking, Susskind argued. It was a consequence of string theory. It was demanded by the deepest mathematics we had, and if Hawking could not see that, perhaps he had lost his edge. The physics community watched, fascinated and a little horrified, as two of its brightest stars circled each other like duelists. Let me try to give you a feel for what was at stake. Imagine that everything you have ever experienced, every sight, every sound, every memory, every thought, was recorded somewhere. Not in your brain, necessarily, not in any physical object you could point to, but somewhere, encoded in the fabric of reality itself. This is what quantum mechanics seems to promise. The universe, at its most fundamental level, is a vast accounting system. Nothing is ever truly lost. Every interaction leaves a trace. Every particle remembers, in some sense, every other particle it has ever touched. Now imagine that somewhere in the universe there is a machine that erases, a mechanism that takes those traces and wipes them clean, a process that does not just hide information, but deletes it, permanently, irreversibly, beyond any possibility of recovery. If such a mechanism exists, then the universe is not an accounting system after all. It is something else, something more forgetful, something that allows facts to slip away into genuine oblivion. Hawking was saying black holes were that mechanism. Susskind was saying they could not be. That if they were, everything we thought we knew about quantum mechanics, every experiment we had ever done, every prediction we had ever confirmed, was built on a lie. The difference was not just philosophical. If Hawking was right, quantum mechanics was an approximation that broke down at extreme energies. We might need to rebuild physics from scratch. If Susskind was right, our understanding of space itself was fundamentally wrong. But quantum mechanics at least would survive. Neither option was comfortable, but one of them had to be true. The holographic principle, in the years after Susskind proposed it, began to gather support. Part of this was theoretical. Juan Maldacena, an Argentine physicist working at Harvard, discovered in 1997 a precise mathematical relationship between certain string theories and certain quantum theories. The string theories lived in a higher dimensional space with gravity. The quantum theories lived on the boundary of that space without gravity. And Maldacena showed that these two theories, which looked completely different, which described different numbers of dimensions, which seemed to have nothing in common, were actually identical. Two languages for the same underlying reality. This was the first concrete example of holography in action. A quantum theory on a boundary could fully encode a gravitational theory in the interior. The lower dimensional description was not an approximation. It was complete. Maldacena's discovery electrified the physics community. Suddenly, the holographic principle was not just an intuition or a hope. It was a theorem, a proven fact about at least some quantum gravitational systems. But Hawking was not convinced. The systems Maldacena studied were abstract, mathematical playgrounds designed to be solvable, not realistic models of the universe we live in. Black holes in Maldacena's world were not the same as black holes in our world. The horizons were different. The boundary conditions were different. Everything was different. Hawking argued that these toy models told us nothing about real physics. They were interesting mathematics, yes, but they were not the universe. And in the universe, in the actual physical cosmos we inhabit, information could still be lost. Susskind countered that Hawking was missing the point. The precise details of Maldacena's models did not matter. What mattered was the principle. If holography worked anywhere, it probably worked everywhere. And if information was preserved in any quantum gravitational system, it was probably preserved in all of them. The debate continued, the papers multiplied, and somewhere in the background the universe itself waited to render its verdict. Here is something that most people do not understand about physics. Theories do not win arguments. Nature does. You can have the most beautiful mathematics in the world. You can have the most elegant reasoning, the most compelling intuitions, the most distinguished supporters. But if nature disagrees, you are wrong, and there is no appeal. The problem with the black hole information paradox was that nature was silent. No one had ever observed Hawking radiation directly. No one had ever watched a black hole evaporate. No one had ever run an experiment that could distinguish between information loss and information preservation. The entire debate was, in a sense, theoretical, a battle of mathematical frameworks, fought in the language of equations and thought experiments. But thought experiments in physics are not just games. They are how we push our theories to their limits. They are how we discover contradictions. And in the late 1990s, a series of thought experiments began to stack the deck against Hawking. One of the most famous was called the AMPS paradox, after the four physicists who proposed it in 2012, Almeri, Marolf, Polkinski, and Sully. The details are technical, but the conclusion was stark. If you assumed information was truly lost in black holes, you were forced to accept one of three consequences. Either the laws of quantum mechanics broke down near the horizon, or the interior of the black hole did not exist, or an observer falling into a black hole would be incinerated by a firewall of high-energy particles at the very moment they crossed the event horizon. None of these options was acceptable to Hawking. The first contradicted his own mathematics. The second sounded like Susskind's holography, which he rejected. The third was absurd. General relativity clearly predicted that an observer falling into a large black hole would notice nothing special at the horizon. They would simply drift through, experiencing the gentle pull of gravity, unaware that they had passed the point of no return. The paradox was a trap, and Hawking was caught in it. The years that followed were difficult ones for Hawking's position. One by one, the theorists who had supported information loss began to defect. Gerard 't Hooft, a Nobel laureate who had been among the earliest skeptics of quantum mechanics' sacred principles, started to waver. Even Hawking's own students began to question whether their mentor had gotten this one wrong. The mathematics was relentless. Every attempt to save Hawking's picture, every modification, every caveat, every clever workaround, ran into the same problem. It required breaking something else: quantum mechanics, general relativity, the basic structure of space and time. Nothing could be preserved while abandoning information, and the holographic principle kept working. Maldaceno's correspondence found application after application. Physicists used it to calculate properties of black holes, of quark-gluon plasmas, of superconductors. It was not just a curiosity anymore, it was a tool. Still, Hawking held out. There is something admirable about this, and something frustrating. Hawking was not stubborn by temperament. He had changed his mind before, famously conceding a bet about whether naked singularities could exist. But information loss was different. It was his discovery, his paradox. The idea that his own calculation had led him astray was hard to accept, and perhaps he was right to hold out. Perhaps the physics community was moving too fast, seduced by mathematical elegance rather than physical truth. Perhaps the holographic principle would eventually be shown to be a mirage, a property of artificial models, not the real universe. But the evidence kept piling up, and by the mid-2000s the weight of it had become unbearable. The turning point came in 2004 at a conference in Dublin. Stephen Hawking took the stage. He was 72 years old. He had lived more than 40 years past his original prognosis. He had written best-selling books, become a cultural icon, inspired a generation of physicists and dreamers. And now he was about to do something that Stephen Hawking almost never did. He was about to admit he was wrong. The talk was titled Information Loss in Black Holes. But the content was the opposite of what that title might suggest. Hawking had recalculated. He had reconsidered. He had found a way, a subtle, technical way, involving quantum corrections to the geometry of the event horizon, for information to escape after all. I want to report that I think I've solved a major problem in theoretical physics, Hawking announced, his synthesized voice echoing through the lecture hall. I have been working on this problem for the last 30 years, and I now have a new answer. The answer was that Susskind had been right. Information was not destroyed. It was encoded on the horizon, scrambled beyond recognition, but ultimately preserved. When a black hole evaporated, it did not erase the past. It released it, particle by particle, in the thermal glow of Hawking radiation. The universe, after all, had a memory. Hawking did not use the word hologram in his talk. He did not endorse every detail of Susskind's picture, but he conceded the essential point. The principle of quantum mechanics was not broken by black holes, it was vindicated by them. The audience sat in stunned silence. Some of them had spent decades on one side of this debate. Some had built careers defending Hawking's original position, and now, in a single hour, the ground had shifted beneath them. Susskind was not in the room that day. He heard the news later from a phone call from a colleague who could barely contain his excitement. "He said it," the colleague reported. "He said you were right." Susskind's reaction was not what you might expect. He did not gloat. He did not celebrate. He felt something closer to relief, and oddly, a kind of sadness. The war was over, but it had taken 20 years. It had consumed careers, it had divided friendships, and the prize, the answer, had been there all along, waiting to be found. Let that settle for a moment. What does it mean to say the universe is a hologram? It does not mean you are living in a simulation. It does not mean reality is fake. It does not mean that anything you experience is less than fully real. What it means is stranger, and in some ways more beautiful. It means that the deepest description of reality, the most fundamental level of physics, the place where all the laws come from, may not be three-dimensional at all. It may be two-dimensional, a flat surface infinitely far away on which every fact about the interior of space is somehow written. The interior is real. You are real. But you are also, in some sense, a projection, a reconstruction, a pattern that the universe holds in its memory, even as you move and breathe and think. This is not metaphor. This is not poetry dressed up as science. This is what the mathematics says, and the mathematics, as far as we can tell, does not lie. The holographic principle has not been proven for our universe. The calculations that established it rigorously apply only to certain idealized systems, systems with different dimensions, different boundary conditions, different properties than the cosmos we inhabit. But physicists increasingly believe that something like holography must be true even here, that the lessons learned in those toy models are telling us something deep about the nature of space and time and information. If they are right, then Susskind's chalkboard in 1997 was not just an idea, it was a window, a glimpse of a truth so strange that even the man who proposed it did not fully understand it. And Hawking, for all his resistance, was not wrong to push back. His skepticism forced the field to sharpen its arguments, to close its loopholes, to earn its conclusions through rigour rather than hope. Without Hawking's opposition, the holographic principle might have remained a speculation, an interesting idea, never tested, never refined. The war made both sides stronger, and the universe, as always, waited patiently for us to figure it out. But the story does not end with Hawking's concession, because even now, more than a decade after Hawking's death in 2018, physicists are still arguing about what the holographic principle really means. They are still struggling to understand how a two-dimensional surface can encode a three-dimensional world. They are still searching for the precise mechanism by which information escapes a black hole, whether it leaks out slowly or bursts out at the end, or tunnels through space-time in some way we cannot yet imagine. And they are still asking the hardest question of all. If the universe is a hologram, where is the projector? Where is the boundary on which our reality is written? How far away is it? What is it made of? Could we ever reach it, touch it, understand it? Or is it forever beyond our grasp? A horizon that recedes no matter how far we travel? These questions remain unanswered. They may remain unanswered for centuries, but they are the questions that Susskind and Hawking bequeathed to us. The questions that emerged from their 20-year war, like mountains pushed up by colliding continents. The debate over information loss was not just about black holes. It was about whether the universe makes sense, whether the rules that govern the smaller scales are consistent with the rules that govern the largest, whether reality, at its foundation, is coherent, or whether it is a patchwork of incompatible truths, a house divided against itself. Susskind and Hawking, in their different ways, both believed in coherence. They both believed that physics should hang together. They just disagreed about which pieces would have to give. In the end, it was space itself that gave. Space which feels so solid, so absolute, so obviously three-dimensional. Space turned out to be the expendable piece, the piece that could be rebuilt from something simpler, the piece that was perhaps never quite as real as we thought. That is a strange thought to carry with you into sleep. The room you are lying in, with its walls and its ceiling and its depth, all of it might be encoded on a surface you will never see. All of it might be, in the deepest sense, a kind of memory, a pattern held in the mind of the cosmos. But here is the comforting part. Even if you are a hologram, you are a very good hologram. You feel real because, for all practical purposes, you are real. The projection is so perfect, so complete, so faithful to every law of physics you have ever experienced, that no experiment you could ever perform would reveal the trick. You're not diminished by holography. You're revealed by it. You're a window into a deeper truth, a truth that Susskind glimpsed on that chalkboard in 1997, that Hawking fought for 20 years before finally accepting, that physicists today are still struggling to understand. The universe, it turns out, is more efficient than we imagined. It stores its information more cleverly. It uses less space, literally less space, than we thought possible. And somehow, out of that elegance, it builds you. Rest with that for a moment. There is more to tell. The details of Maldaceno's correspondence, the resolution of the firewall paradox, the ongoing debates about what happens at the singularity, at the centre of a black hole, where even the holographic principle has not yet reached. But those are stories for later sections of this journey. For now, it is enough to sit with the image. Two men, one in a wheelchair speaking through a machine, one standing at a chalkboard, chalk dust on his fingers, 20 years between them, filled with papers and conferences and arguments and grudging respect. And at the end, a single answer. The universe remembers. Nothing is ever truly lost. And somewhere, on a boundary we cannot see, every fact about this moment, about you, listening, about the dark of the room and the hum of the device and the slow drift towards sleep, is written. You are part of that record. You always have been. You're part of that record. You always have been. And now we must go back. Back before the resolution. Back before Maldacina's paper changed everything. Back to the years when Susskind and Hawking were still at war, when the physics community was split down the middle, when the very coherence of quantum mechanics seemed to hang by a thread. Because the story I have told you so far, the story of holography, of information preserved, of a universe that remembers, that story only makes sense if you understand what it cost to get there, what it cost to believe, what it cost to fight for an idea that most of your colleagues thought was wrong. Let me take you back to 1993. Leonard Susskind is in his office at Stanford, and he is furious. Not shouting furious, not throwing things. Susskind is a calm man, methodical, the kind of physicist who thinks in pictures and builds his arguments like a bricklayer builds a wall, one carefully placed piece at a time. But underneath that calm, something is burning. Because he has just read Stephen Hawking's latest paper, and he cannot believe what he is seeing. Hawking is doubling down. For almost 20 years, ever since his original 1975 calculation, Hawking has been claiming that black holes destroy information, that when matter falls into a black hole and the black hole eventually evaporates through Hawking radiation, the information about that matter, its quantum state, its precise configuration, everything that made it what it was, vanishes from the universe, not hidden, not scrambled beyond recognition, destroyed, gone in a way that violates the most fundamental principle of quantum mechanics. And now, in 1993, Hawking is not backing down. He is going further. He is arguing that this information loss is not a bug but a feature, that it reveals something deep about the incompatibility between quantum mechanics and gravity, that the universe, at its foundation, is simply not as coherent as we believed. Susskind reads this, and he feels something like vertigo, because if Hawking is right, then everything Susskind has spent his career believing is wrong. The unitarity of quantum mechanics, the principle that information is always preserved, that the universe keeps perfect records, would be just an approximation, a useful fiction that breaks down in extreme conditions, and that would mean that physics, at its deepest level, does not make sense, that there are situations where the past cannot be reconstructed from the present, where the fundamental laws contradict each other, where the universe forgets. Susskind cannot accept this, not because he is stubborn, not because he dislikes Hawking, but because he has spent 30 years watching quantum mechanics predict the results of experiments with impossible precision. He has seen it work at 12 decimal places. He has seen it describe phenomena that no one expected, phenomena that seem to violate common sense, and every single time the predictions have held. Every single time the universe has turned out to obey the rules. And now Hawking is telling him that all of that breaks down at the edge of a black hole, that there is a place in the universe where the rules stop working, that the impossible precision of quantum mechanics is built on a foundation of sand. Susskind does not believe it. More than that, he will not believe it until someone shows him exactly where his reasoning is wrong, until someone takes his argument for information preservation and finds the flaw, the hidden assumption, the place where he has made a mistake. Because Susskind has an argument, a good argument, an argument that says information must be preserved, that unitarity cannot be violated, that Hawking's calculation, as beautiful as it is, must be missing something, and so begins the war. Picture what it meant to oppose Stephen Hawking in 1993. Hawking was not just a famous physicist. He was, in many ways, the face of theoretical physics itself. His book, A Brief History of Time, had sold millions of copies. His face was recognized around the world. His story, the brilliant mind trapped in a failing body, the voice synthesized by machine, the wheelchair that became a kind of throne, had made him a symbol of human resilience and intellectual triumph. To argue with Hawking was to argue with an icon, and Hawking was not just famous, he was formidable. Behind the synthesized voice was one of the sharpest minds in physics, a mind that had revolutionized our understanding of black holes and cosmology, a mind that had made discoveries that would still be taught 1,000 years from now. When Hawking said that information was lost, the physics community listened. When Hawking published a paper, people read it carefully. When Hawking defended his position at conferences, people took notes. Susskind knew all of this. He knew the weight of the name he was challenging, and he also knew something else, something that gave him the courage to keep fighting, even when most of his colleagues thought he was wrong. He knew that Hawking had not proven his case. This is a subtle point, but it is crucial. Hawking's 1975 calculation was a masterpiece. It showed that black holes emit radiation, that they have a temperature, that they slowly evaporate over time. All of that was solid. All of that has held up for 50 years. But the claim that information is destroyed, that specific claim, was not derived from the calculation. It was an interpretation, a conclusion that Hawking drew from his results, but not a result that was forced by the mathematics. The mathematics said that black holes radiate. The mathematics said that the radiation is thermal, random, featureless, carrying no information about what fell in. But the mathematics did not say why the radiation was thermal. It did not say whether the information was truly gone or merely hidden. It did not say whether, with a better understanding of quantum gravity, the information might somehow be preserved. Hawking believed the information was gone. He believed it because his calculations seemed to leave no room for it. The radiation came out thermal, and thermal radiation carries no memory. Therefore, he concluded, the memory was destroyed. But Susskind saw another possibility. What if the radiation only appeared thermal? What if the information was there, encoded in subtle correlations between the particles? Correlations too delicate to detect with current tools, but real nonetheless. What if the black hole was like a locked safe, seemingly featureless on the outside, but holding its secrets within, waiting for the right key? This was not a proof. Susskind did not have a calculation that showed information was preserved. He had an intuition, a conviction, a refusal to believe that quantum mechanics could fail. He had the feeling that there must be a way out, that the universe must make sense, that somewhere in the mathematics there was a resolution waiting to be found. And so he began to search. Let me try to give you a feel for what that search looked like. Imagine you are a detective and you have been presented with a crime scene that violates the laws of physics, a locked room, a body inside, no doors, no windows, no way in or out. And yet, the body is there. The murder happened. The evidence is undeniable. You have two choices. You can accept that the laws of physics were violated, that somehow, impossibly, the killer walked through walls. Or you can insist that the laws hold and keep looking for the hidden passage, the secret door, the tunnel that no one has found yet. Susskind chose the second path. He kept looking for the hidden passage. He kept insisting that quantum mechanics was right, that unitarity was sacred, that somewhere in the black hole there was a mechanism that preserved information even as it scrambled it beyond recognition. And for years, for almost a decade, he could not find it. This is the part of the story that often gets left out. The years of failure, the years of searching, the years of writing papers that proposed mechanisms, only to have those mechanisms shot down. The years of attending conferences where Hawking would present his case calmly and confidently, and Susskind would present his countercase stubbornly and desperately, and neither side would convince the other. Do you know what it is like to fight for an idea that you cannot prove? There is a special kind of loneliness in that fight. You're not wrong, you can feel that you're not wrong in your bones, in the way the mathematics almost works, in the way every alternative seems to lead to absurdity. But you cannot show that you are right, you cannot produce the calculation that settles the question. You cannot point to the hidden passage and say, there, that is how the killer got in, that is how information escapes. All you can do is keep searching, keep proposing, keep refusing to give up, and Susskind did. But Susskind was not alone in this fight. He had allies, other physicists who shared his conviction that information must be preserved, and he had one ally in particular who would prove crucial in the years to come. His name was Gerard de Hooft. 'T Hooft was a Dutch physicist, a Nobel laureate, one of the architects of the standard model of particle physics. He was, by any measure, one of the greatest physicists of the 20th century, and he too refused to accept that black holes destroyed information. In fact, 't Hooft went further than Susskind. In 1993, the same year that Hawking was doubling down on information loss, 't Hooft published a paper that proposed something radical, something that seemed at first almost absurd. He proposed that the universe might be a hologram, not a hologram in the science fiction sense, not a projected image that you could walk through, not an illusion that could be switched off. A hologram in the mathematical sense, a system where all the information in a three-dimensional region could be encoded on a two-dimensional surface. A system where depth was not fundamental, where the third dimension was, in some sense, a reconstruction from data stored in fewer dimensions. Hooft called it the holographic principle, and when Susskind read 't Hooft's paper, something clicked. He had been searching for the hidden passage, the mechanism that preserved information as it fell into a black hole. And here, in 't Hooft's proposal, was the beginning of an answer. What if the information never really fell in at all? What if, from the right perspective, the information stayed on the surface? What if the three-dimensional interior of the black hole was, in some deep sense, a projection, and the real record, the true data, was written on the two-dimensional horizon? This was a strange idea, a disorienting idea, an idea that seemed to violate everything we knew about space and geometry, but it was also an idea that preserved unitarity. It was an idea that saved quantum mechanics, and that, for Susskind, was enough. He began to develop the holographic principle. He began to work out what it would mean for a three-dimensional universe to be encoded on a two-dimensional surface. He began to ask the questions that would eventually lead to Maldaceno's breakthrough. The questions about how information could be stored, how it could be retrieved, how a hologram could be so perfect that no experiment inside it could ever detect the trick. And all the while, Hawking kept fighting. Because Hawking was not convinced. Hawking looked at the holographic principle and saw speculation. He looked at Susskind's arguments and saw hand-waving. He looked at the claim that information was preserved and asked the obvious question: where? Where exactly is this information? How exactly does it get encoded on the horizon? How exactly does it get imprinted on the outgoing radiation? Show me the calculation. Show me the mechanism. Show me the math. And Susskind in the early 1990s could not show him. This is where we must pause and appreciate the difficulty of the problem. Susskind had an intuition, he had a principle, he had a direction, but he did not have a theory. He did not have a concrete mathematical framework that would let him calculate what happened to information as it fell into a black hole. He did not have a model that would tell him, step by step, how the data got transferred from the interior to the surface. And without that model, Hawking was right to be skeptical. Science is not settled by intuition. It is not settled by philosophical arguments, however compelling. It is settled by calculation, by prediction, by mathematics that can be checked, tested, compared against alternatives. And in the early 1990s, the mathematics was on Hawking's side. His calculation was concrete. His result was clear. His prediction, that information was lost, followed directly from his equations. Susskind's counter-argument was, at that point, more like a hope than a proof. But Susskind did not give up. He could not give up, because the alternative, accepting that quantum mechanics was violated, accepting that the universe was incoherent at its foundation, was simply too terrible to contemplate. And so he kept working, kept thinking, kept searching for the mathematics that would vindicate his intuition. The years passed, the 1990s unfolded, the physics community watched and waited, papers were published, conferences were held, arguments were refined, and slowly, gradually, the tide began to turn. Not because Susskind found the final answer, that would come later, with Maldacena, but because other physicists began to join his side, because the arguments for information preservation began to accumulate, because the alternatives, the theories in which information was truly lost, began to seem more and more problematic. You see, Hawking's proposal had consequences. If information was destroyed in black holes, then quantum mechanics would have to be modified. The equations that had worked so perfectly for so long would need to be changed. And every attempt to make that change led to trouble. Every modified theory either predicted outcomes that were obviously wrong, or introduced new problems that were even worse than the original paradox. Meanwhile, the holographic principle, strange as it was, kept looking more and more plausible. String theorists found hints of it in their equations. Calculations in lower dimensions suggested that it might work. The idea that space was not fundamental, that the third dimension was emergent, began to seem less crazy and more inevitable. This is how science often works, not with a single decisive experiment, but with a gradual accumulation of evidence, a tipping point that is only visible in retrospect, a moment when the balance shifts, when the burden of proof changes, when the once radical idea becomes the new consensus. For the information paradox, that tipping point came in 1997. But before we get there, before we reach Muldacina's paper and the resolution that changed everything, we must spend a moment longer in the years of uncertainty, the years when the outcome was not clear, the years when Susskind and Hawking were still genuinely at war, when neither side had won, when the future of physics hung in the balance. Because those years matter. They matter because they remind us that science is not a smooth march toward truth. It is a struggle, a contest, a series of bets placed against the unknown, with careers and reputations on the line. Susskind bet his on information preservation. Hawking bet his on information loss. And for 20 years, neither could prove the other wrong. That is a long time to fight for an idea, a long time to defend a position that you cannot prove, a long time to attend conferences and answer the same objections and watch your opponent smile and say, calmly and confidently, that you are mistaken. Susskind later described those years as the hardest of his career, not because the physics was difficult, though it was, but because the stakes were so high, because he knew with a certainty he could not justify that quantum mechanics was right, that the universe made sense, that somewhere in the black hole there was a mechanism that saved coherence. And he had to keep believing that, year after year, in the face of one of the greatest minds in physics telling him he was wrong. Let that settle for a moment, because this is not just a story about physics, it is a story about conviction, about the courage to defend an idea against overwhelming opposition, about the stubbornness that science sometimes requires, the willingness to be wrong, to look foolish, to stake your reputation on a hunch that might never pay off. Susskind had that stubbornness. Hawking had it too in his own way. They were both gamblers, betting everything on their vision of how the universe worked. And for 20 years neither blinked. In the end, of course, one of them was right and one was wrong. The universe does remember. Information is preserved. The holographic principle, strange as it seemed, turned out to be the key. But that resolution was still years away when Susskind first read 't Hooft's paper in 1993. It was still years away when Susskind began developing his own version of holography, when he started writing papers about black hole complementarity, when he proposed that an observer falling into a black hole might see something completely different from an observer watching from outside. Black hole complementarity. That is an idea we have not yet explored. It is strange enough that it deserves its own moment. Picture this. An astronaut falls into a black hole. From her perspective, nothing special happens at the horizon. She crosses it smoothly, just as she would cross any other invisible boundary in space. She continues falling, deeper and deeper, until she reaches the singularity at the center, a point of infinite density where our equations break down and we do not know what happens next. But now picture what an observer outside the black hole sees. To that outside observer, the astronaut never crosses the horizon at all. Instead, she appears to slow down as she approaches the boundary, her image stretching and reddening, her clock ticking slower and slower, until she seems to freeze at the very edge, never quite crossing, never quite falling in. This is not an illusion. This is not a trick of perspective. According to general relativity, both descriptions are correct. The astronaut really does fall through, from her point of view, and she really does freeze at the horizon, from the outside point of view. The two descriptions are different, but they are both true. Now here is where Susskind got clever. He proposed that the same logic might apply to information. From the astronaut's perspective, the information she carries falls into the black hole with her. It crosses the horizon, it enters the interior. From the outside observer's perspective, that information never crosses the horizon at all. Instead, it gets smeared across the surface, encoded in the subtle fluctuations of the boundary, preserved forever even as the black hole slowly evaporates. Both descriptions are true, both are valid, and there is no contradiction, because no single observer can ever see both. The astronaut cannot report back from inside the black hole. The outside observer cannot dive in and check. The two perspectives are complementary. They are like two different maps of the same territory, each useful in its own domain, each incomplete, each telling a different part of the truth. This was black hole complementarity, and it was brilliant. Not because it solved the information paradox completely, it did not. There were still questions, still gaps, still places where the mathematics was not worked out. But it showed that there might be a way to reconcile quantum mechanics with general relativity. It showed that the contradiction might be apparent, not real. It showed that with enough cleverness, with the right perspective, the universe might make sense after all. Hawking was not convinced. He looked at black hole complementarity and saw philosophy, not physics. He asked the hard questions. What is the actual mechanism? What is the equation? How do you calculate? And Susskind in those early years did not have satisfying answers, but the idea took root. Other physicists began to work on it. The holographic principle spread through the community, fertilizing new research, inspiring new calculations, pointing toward a resolution that was still just out of reach. And then came 1997. Then came Juan Maldacena. Then came the paper that changed everything. But that is a story for the next stretch of this journey. For now, rest with what we have covered. The early years of the war, the conviction that drove Susskind, the skepticism that drove Hawking, the holographic principle, emerging from Tufte's imagination like a strange new continent rising from the sea, the idea of black hole complementarity, suggesting that contradictions might be resolved through perspective. These were the building blocks, these were the pieces that would eventually fit together. And in 1997, a young physicist from Argentina would take those pieces and build something extraordinary. A correspondence, a duality, a mathematical proof that the universe really could be a hologram. That proof was coming. It was almost here. And when it arrived, even Hawking would eventually have to change his mind. The year is 1997. Juan Maldacena is 30 years old. He has dark hair, a quiet voice, and a habit of filling blackboards with equations that most of his colleagues cannot follow. He was born in Buenos Aires, trained in Argentina, came to the United States for graduate school, and now sits at Harvard as a young professor with a reputation for brilliance and an unusual tolerance for mathematical pain. He has been thinking about black holes. He has been thinking about string theory. He's been thinking about the holographic principle, about the strange suggestion that information might be encoded on boundaries, about the way physics at the edge of a region might somehow contain everything that happens inside. And in November of that year, at a conference in Santa Barbara, he stands before a room full of the world's leading theoretical physicists and presents a paper that will reshape the landscape of physics for the next 3 decades. The paper has a dry title. It is called The Largen Limit of Superconformal Field Theories and Supergravity. The title tells you almost nothing about what it contains, but the content is revolutionary. Maldacena has found something that no one expected. He has found a precise mathematical correspondence, a dictionary, a translation, between 2 completely different theories. On one side of the correspondence sits a theory of gravity in 5 dimensions, a curved space-time that includes the kinds of objects string theorists had been studying for years. On the other side sits a quantum field theory in 4 dimensions, a theory that describes particles and forces on a flat boundary, a theory that contains no gravity at all. And Maldacena showed that these 2 theories are not just similar, they are not just related, they are the same. Every calculation you do in one theory can be translated into a calculation in the other. Every physical prediction matches, every observable agrees. The 5-dimensional universe with gravity is completely equivalent to the 4-dimensional universe without gravity. They are 2 descriptions of the same underlying reality, like a hologram and the scene it depicts, like a shadow and the object that casts it. This was the ADS-CFT correspondence. The letters stand for anti-de Sitter space on one side, a particular kind of curved space-time with negative cosmological constant and conformal field theory on the other, a particular kind of quantum theory that respects certain symmetries. The technical details are formidable, the mathematics is dense, but the conceptual payoff is staggering. Let that settle for a moment. What Maldacena had done was prove, not suggest, not hint, but prove, mathematically, that the holographic principle could work, that a universe with gravity in a certain number of dimensions could be completely described by a theory without gravity living on its boundary, that the interior could be reconstructed from the surface, that the volume could be encoded on the edge. He had not done this for our universe, not yet. The space-time in his correspondence was not quite like ours. It had different properties, different curvature, different rules. But that almost did not matter. What mattered was that the principle worked. What mattered was that the correspondence was exact. What mattered was that you could take one theory, translate it into the other, and get the same answers. Imagine you're learning a new language. Someone tells you that French and Spanish are related, that if you know one you can learn the other more easily, that there are cognates and shared roots and similar grammatical structures. That is useful information. But now imagine someone hands you a perfect translation machine. Put in any sentence in French, and out comes the exact equivalent in Spanish. Not approximately equivalent, not close enough. Exactly the same meaning, guaranteed by mathematical proof. That machine would change everything. You could solve problems in whichever language was easier. You could check your work by translating back and forth. You could study difficult French grammar by looking at the simpler Spanish equivalent, or vice versa. That is what Maldacena gave the physics community, a translation machine between gravity and quantum mechanics, a dictionary between space-time and information, a proof of concept that the holographic principle was not just poetry, it was physics. The response was immediate. Within months, hundreds of physicists had dropped what they were working on and started exploring the new correspondence. Within years, thousands of papers had been written. New techniques emerged. Old problems became tractable. Questions about black holes that had seemed impossibly hard suddenly had paths forward, because you could translate them into a different language where the calculations were easier. Consider the information paradox again. In the original formulation, you had to track what happened to information as it fell into a black hole, and the black hole evaporated. That required understanding quantum gravity in its full glory, understanding the interior of the black hole, understanding Hawking radiation, understanding how information could be preserved through a process that seemed designed to destroy it. These were hard problems. They involved regimes where we had no reliable mathematical tools. But in the AD-CFT correspondence, the black hole on the gravity side translates to a different kind of object on the field theory side. A black hole in the 5-dimensional space-time corresponds to a hot thermalized state of the quantum field theory in 4 dimensions, and the field theory has no gravity. It has no horizons. It has no singularities. It is, in a certain sense, much simpler than the gravity theory. The equations are well defined, the calculations can be done, and the field theory is manifestly unitary. Information is preserved. There is no paradox on the field theory side. The laws of quantum mechanics work exactly as they should, which means, by the translation, that information must also be preserved on the gravity side. It cannot be destroyed by black holes. The paradox is resolved, not by finding a specific mechanism, not by tracking the information bit by bit, but by proving that any such mechanism must exist, because the translated theory demands it. This was not a philosophical argument. This was not hand-waving. This was mathematics. If the correspondence is correct, and by now, after decades of testing, the evidence for the correspondence is overwhelming, then Hawking was wrong. Information is preserved. Quantum mechanics wins. The paradox dissolves. Susskind understood immediately what Maldacena had done. He had been working towards something like this for years, building the conceptual foundations, developing the holographic principle, constructing black hole complementarity. But Maldacena had supplied the proof. Maldacena had shown that the holographic principle was not just a possibility but a reality, at least in this particular mathematical setting. The young physicist from Argentina had done what the older generation had not quite managed. He had turned intuition into theorem. And Hawking? Hawking took notice. He had to. The physics community was reorganizing itself around Maldacena's discovery. The evidence was mounting. The calculations were working. Paper after paper confirmed the correspondence, extended it, tested it, found it holding up under every examination. By 2004, Hawking would publicly concede the bet he had made with Kip Thorne and John Preskill years earlier. the bet about whether information could escape from black holes. He admitted he had been wrong. He paid up with an encyclopedia, the prize that had been agreed upon, though not before writing his own paper, attempting to explain how information might be recovered through subtle correlations in the Hawking radiation itself. But that concession was still 7 years away when Maldacena presented his paper. In 1997, Hawking was sceptical. The correspondence was new, the evidence was still accumulating, and Hawking, above all, was a contrarian. He did not give up his positions easily. He had built his reputation on being willing to challenge established thinking, and now that the establishment was shifting toward the holographic principle, part of him resisted. Not out of stubbornness, or not only out of stubbornness, but out of scientific caution. The correspondence worked for anti-de Sitter space fine, but our universe is not anti-de Sitter space. Our universe has a positive cosmological constant, not a negative one. Our universe is expanding, not bounded. To Hawking, the leap from Maldacena's idealized setting to our actual cosmos was a leap too far, at least until someone could show how to make the translation for real space-time. He was not wrong to raise these concerns. They remain open questions even now. The AD-CFT correspondence is a proof of concept, not a proof of the way our particular universe works. It shows that holography is possible. It does not show that our universe is a hologram. That distinction matters. That distinction is part of what kept the debate alive even after Maldacena's triumph. But the momentum had shifted. The burden of proof had changed. Before Maldacena, you could reasonably say that the holographic principle was speculation, that information preservation was wishful thinking, that quantum mechanics might break down at black hole horizons and we just had to accept it. After Maldacena, that became much harder to maintain. You now had a concrete, calculable, testable framework in which holography worked and information was preserved. If you wanted to argue that our universe was different, you had to explain why. You had to offer an alternative. You had to do more than shake your head and demand better equations. The war between Susskind and Hawking did not end with Maldacena's paper. It evolved. The terms of the debate shifted. New battlegrounds opened up. But the shape of the conflict had changed forever. Susskind now had his heavy artillery. He had a mathematical result that vindicated his intuitions. He had proof that the universe could be a hologram, that information could be preserved, that quantum mechanics could win. He was no longer fighting on faith. He was fighting with theorems. And Hawking, even in his skepticism, even in his resistance, began the slow process of absorbing what Maldacena had shown. He was too good a physicist to ignore evidence forever. He was too honest to cling to a position that the mathematics was abandoning. But he would not go quietly. He would not simply fold. Over the next 7 years, he would continue to probe, to question, to challenge, to offer his own alternative explanations. He would write papers. He would give talks. He would defend his ground, even as that ground eroded beneath him. This is how science works, at its best. Not through sudden conversions, not through overnight revolutions, but through the slow accumulation of evidence, the gradual shifting of probabilities, the patient work of calculation and argument and re-examination. Susskind and Hawking were not enemies, they were sparring partners. They were sharpening each other's ideas against the whetstone of disagreement. And the ideas that emerged from that contest were stronger than either man could have produced alone. Let that settle for a moment. Now consider what the AD-CFT correspondence actually meant, beyond the resolution of the information paradox. Consider the deeper implications of Maldacena's discovery. The correspondence tells us that a theory with gravity can be exactly equivalent to a theory without gravity. It tells us that space-time, the fabric of Einstein's universe, can emerge from something simpler, something more fundamental, something that does not include space-time at all. Think about what that means. Gravity is not fundamental. Space-time is not fundamental. They are emergent phenomena, patterns that arise from deeper structures, shadows cast by a higher dimensional reality. This is a conceptual revolution as profound as anything Einstein discovered. When Einstein developed general relativity, he showed that gravity was not a force in the Newtonian sense. It was the curvature of space-time itself. Massive objects bend the fabric of the universe, and other objects follow those curves. Space and time became dynamical, flexible, responsive to the matter and energy within them. That was revolutionary. But Einstein still treated space-time as fundamental. It was the arena in which physics took place, It was the stage on which all the actors performed. The holographic principle, and its concrete realization in AD-CFT, suggests something even stranger. Space-time is not the stage. Space-time is part of the performance. It emerges from the relationships between quantum degrees of freedom on the boundary. The 3 dimensions of space that we move through, the 1 dimension of time that carries us forward, these are not built into the foundations of reality. They are patterns that crystallize out of something more primitive, more abstract, more quantum mechanical. This is not easy to visualize. We are creatures of 3 spatial dimensions. We cannot picture what it would be like for space itself to be emergent, to arise from something non-spatial. But the mathematics is unambiguous. In the AD-CFT correspondence, the bulk space-time, the 5-dimensional arena with gravity, is constructed from the entanglement structure of the boundary field theory. The more entangled certain parts of the boundary theory are, the shorter the distances between corresponding points in the bulk. The geometry of space-time is encoded in patterns of quantum correlation. Space, at some fundamental level, is woven from the threads of entanglement. This insight has spawned an entire subfield of physics. Researchers now study the emergence of space-time from quantum information. They build tensor networks, mathematical structures that represent how quantum systems can be entangled in particular patterns, and show that these networks can generate geometries, can produce distances and curvatures, can mimic the properties of curved space-time. They explore how the equations of general relativity, Einstein's equations, might be derived from the rules of quantum information theory. They ask whether the universe is not so much a thing made of stuff, as a structure made of relationships, a web of correlations that we perceive as space and time and matter. This work is ongoing. It is incomplete. It does not yet tell us exactly how our universe works, because our universe is not anti-de Sitter space, because the cosmological constant is positive rather than negative, because the boundary theory that might describe our cosmos has not yet been identified. But the direction is clear. The evidence points toward a picture of reality in which the things we take for granted, the 3 dimensions of space, the passage of time, the solidity of objects, the distances between places, are all emergent. They arise from something deeper, and that something deeper is quantum, abstract, informational. We are not the first generation to discover that the universe is stranger than we thought. Ancient astronomers discovered that the Earth was round, not flat. Copernicus discovered that the Earth moved, not the sun. Darwin discovered that species evolved, not created fixed. Einstein discovered that space and time were relative, not absolute. Each discovery pushed back against intuition, against common sense, against the way the world appears to naive observation. And now, perhaps, we are learning that space-time itself is not fundamental, that the stage is part of the show, that the 3-dimensional world we inhabit is a hologram projected from a lower dimensional surface, a shadow on the wall of Plato's cave, a representation rather than a reality. If this is true, what does it mean? What does it feel like to live in a holographic universe? The answer, perhaps surprisingly, is that it feels exactly like this. Nothing changes in your direct experience. You still stub your toe on coffee tables. Light still takes time to reach you from distant stars. Apples still fall from trees. The laws of physics, as we experience them, are encoded faithfully in the hologram. The projection is perfect. There is no flaw, no seam, no place where the illusion breaks down. You cannot tell from inside the hologram that you are inside a hologram. The universe is self-consistent. It does not reveal its own encoding. But there is something strange about this, something vertiginous. If the 3-dimensional world is a projection, then what is doing the projecting? Where is the surface on which the hologram is written? What is the nature of the underlying reality from which space and time emerge? These are open questions. They are the questions that physicists are working on today, in 2025 and beyond. They are the questions that Susskind and Hawking were circling around, even before they had the mathematical tools to ask them precisely. And they are questions that may take another century to answer. Rest with that uncertainty for a moment. Let it sit with you like the darkness beyond a campfire. We do not know what space is made of. We do not know how time emerges. We do not know the fundamental nature of reality. But we know that the question can be asked. We know that there is something to discover. And we know that the path forward runs through quantum information, through entanglement, through the strange duality that Maldacena revealed between gravity and field theory. The war between Susskind and Hawking was, in a sense, a war over these deeper questions. It was a war over whether physics makes sense all the way down, whether the laws of quantum mechanics hold even at the edges of black holes, even at the beginning of the universe, even in the regimes where our theories strain and our intuitions fail. Susskind believed they did. Hawking believed for many years that they might not, and the resolution came not through argument alone, but through mathematics, through the patient work of calculation, through the proof that Maldacena provided. But the war was not over. New puzzles emerged, new controversies arose. The black hole information paradox, it turned out, had not been completely solved. It had been transformed. And the transformation led to even deeper questions, even stranger ideas, even more heated debates. In 2012, 15 years after Maldacena's original paper, a group of physicists published a paper that reignited the entire controversy. They were Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully. They asked a simple question. What does the astronaut actually experience as she falls through a black hole horizon? According to general relativity, she experiences nothing unusual at the horizon. She falls smoothly through. The horizon is a point of no return, but it is not a physical barrier. There are no walls, no boundaries, no forces acting at that location. The horizon is defined only by the fact that once you cross it, you cannot escape. But the crossing itself is gentle. According to the holographic principle and black hole complementarity, this should still be true, at least from the astronaut's own perspective. The information she carries is encoded on the horizon for the outside observer, but for her, everything proceeds normally. The two descriptions are complementary. Neither contradicts the other because no single observer can see both. But Almheri, Marolf, Polchinski, and Sully, AMPS as the group came to be called, showed that this comfortable picture had a problem. If you combine the demands of quantum mechanics with the demands of relativity with the preservation of information, you cannot make all of them consistent. Something has to give. And the thing that might give, the thing they proposed, was the smoothness of the horizon itself. The EMPS paper argued that if information is truly preserved, if quantum mechanics fully holds, then the horizon of an old black hole, one that has been evaporating for a long time, cannot be smooth. Instead, it must be surrounded by a firewall, a wall of high-energy particles, a barrier of burning radiation. The astronaut, falling toward what she expects to be a gentle crossing, would instead be incinerated at the horizon. She would hit the firewall and die, long before reaching the singularity. This was shocking. This was disturbing. This seemed to violate the very principles of general relativity that physicists had trusted for a century. The equivalence principle, the cornerstone of Einstein's theory, says that a freely falling observer should not be able to detect the presence of gravity. The laws of physics should be the same in a falling elevator as in empty space. But a firewall would be detectable. A firewall would kill you. A firewall would mark the horizon as a special place, a physical boundary, a deviation from the smooth fabric of space-time. Susskind was startled. He had spent decades defending the holographic principle, defending complementarity, defending the idea that information is preserved without any drama at the horizon. And now a group of younger physicists, using exactly his own principles, had derived a paradox. They had shown that the pieces did not fit together as neatly as he had believed. The firewall paradox ignited a new round of debate. Physicists took sides, papers flew back and forth, conferences buzzed with argument. Was the firewall real? Could it be avoided? What had gone wrong? Some physicists accepted the firewall. They argued that we simply had to give up on smooth horizons. Quantum mechanics was more fundamental than general relativity, and if they conflicted, quantum mechanics won. The equivalence principle was an approximation, valid in most circumstances but failing at black hole horizons. Others rejected the firewall. They looked for loopholes, for alternative assumptions, for ways to make all the principles consistent. Maybe information was preserved but in a more subtle way. Maybe the entanglement structure was different than AMPS had assumed. Maybe there were new effects from quantum gravity that had not been considered. Susskind himself worked furiously on the problem. In 2013, he and his collaborator Juan Maldacena, the same Maldacena who had started the revolution in '97, proposed a radical idea. They suggested that the wormhole geometry connecting two entangled black holes might be related to the quantum entanglement between them. The geometry of space-time and the structure of quantum information were not just analogous, they might be the same thing. They coined a slogan, ER equals EPR. ER for Einstein-Rosen, the physicists who first described wormholes. EPR for Einstein-Podolsky-Rosen, the physicists who first highlighted quantum entanglement. Wormholes and entanglement were, perhaps, two different descriptions of the same underlying connection. This was speculative. This was not proven. But it suggested a possible path forward. If space-time geometry really is built from entanglement, then perhaps the firewall paradox could be resolved by understanding that geometry more deeply. Perhaps the contradiction was not a sign that physics was broken, but a sign that our understanding of space and time was still incomplete. Hawking, by this point, was elderly and ill. He communicated through his speech synthesizer, slowly and laboriously, but he still followed the debates. He still had opinions. In 2014, he published a paper suggesting his own resolution to the firewall paradox. He argued that black hole horizons might not be sharply defined, that the very concept of a fixed horizon might be an approximation that breaks down when you look closely enough, that the information might be preserved through a mechanism that smears out the boundary between inside and outside. It was classic Hawking, provocative, contrarian, challenging the assumptions that everyone else was making. He was 82 years old, in failing health, and he was still fighting, still questioning, still refusing to accept that any problem was truly solved until every last detail was understood. Susskind, meanwhile, continued his own research. The war between them had mellowed with age. They had known each other for decades. They had argued at conferences, exchanged letters, debated in print. But there was respect underneath the disagreement. There was a shared commitment to the same questions, even when they reached different answers. And underneath all the debate, underneath the firewalls and the wormholes and the holographic encodings, there was a deeper story. A story about the nature of reality. A story about what the universe is made of. A story about whether physics makes sense all the way down. That story is not finished. It will not be finished for a long time. The questions that Susskind and Hawking fought over are still open. The puzzles they grappled with are still unsolved. But the shape of the landscape has changed. The holographic principle has moved from speculation to established framework. The AD-CFT correspondence has become a tool that physicists use every day. The idea that space-time might be emergent, built from quantum information, has taken root and grown. We live in a strange universe, stranger than anyone suspected when Susskind and Hawking first began their war, stranger perhaps than we can fully comprehend even now. But the strangeness is not chaos, it is order, waiting to be discovered. It is pattern, hidden beneath the surface. It is meaning, encoded in the mathematics, waiting for the patient and the clever to decode. The fire still burns, the darkness still stretches, and the conversation continues, long into the night. The conversation continues. But to understand where it leads, we need to step back from the mathematics for a moment. We need to ask a different kind of question. Not how the holographic principle works, not what equations describe it, but what it means. What does it mean to say that the universe might be a hologram? What does that claim actually contain? Because the word itself is misleading. When most people hear hologram, they think of science fiction. They think of flickering projections, of Princess Leia pleading for help, of entertainment devices that create the illusion of 3 dimensions from a flat source. They imagine that the holographic principle is saying something like that we are illusions, that we are projections, that the solid world around us is somehow fake, a trick of light, a simulation running on some hidden screen. That is not what physicists mean. Not even close. The holographic principle is not a statement about illusion. It is a statement about information, about where information lives, about how much information a region of space can contain. And when you understand it properly, it is not a claim that diminishes reality. It is a claim that deepens it. It is a claim that says the fabric of existence is woven from threads we are only beginning to see. Let me try to explain. Start with a simple question. How much information can you store in a box? At first, this seems like it should depend on the volume of the box. A bigger box should hold more information, Fill the box with hard drives, with books, with inscribed atoms, with whatever storage medium you like. Double the size of the box and you should be able to store twice as much. Triple it, triple the storage. The information capacity should scale with the volume. But when you bring gravity into the picture, something strange happens. If you try to pack too much information into a region of space, if you squeeze too many bits into too small a volume, you create a black hole. The information collapses under its own weight, and when you work out the mathematics, when you calculate the maximum amount of information that can exist in any region before it collapses, you find that the limit does not scale with the volume. It scales with the surface area, the boundary of the region, not the interior, the skin, not the bulk, the two-dimensional surface, not the three-dimensional volume. This is the Bekenstein bound. Jacob Bekenstein, the same physicist who first proposed that black holes have entropy, derived it in the early 1980s. It says that the maximum information content of any region is proportional to the area of its boundary, measured in units of the Planck area, the smallest meaningful area in quantum gravity, roughly 10 to the minus 66 square centimeters. That number is absurdly small. The Planck area is so tiny that the observable universe, if you covered its entire boundary with Planck scale pixels, would contain something like 10 to the 122nd bits of information. That is an unimaginably large number, but it is still finite, and it is determined by the area, not the volume. Let that settle for a moment. Every region of space has a maximum information capacity. That capacity is determined by the surface, not the interior. The three-dimensional bulk cannot contain more information than can be encoded on its two-dimensional boundary. No matter what you do, no matter how cleverly you pack the data, the boundary wins. This is not speculation. This is not philosophy. This is a mathematical constraint derived from the combination of quantum mechanics and general relativity. It is a feature of how the universe works, and if you take it seriously, it suggests something remarkable. If all the information that describes the interior of a region can be encoded on its boundary, then in a deep sense, the interior is the boundary. The three-dimensional description and the two-dimensional description are not different approximations of the same thing. They are the same thing. Two languages for the same reality. Two representations that contain identical information. The universe is not like a hologram. The universe has the information structure of a hologram. The depth is real. The solidity is real. But the information that defines it lives, in some fundamental sense, on surfaces, on boundaries, on edges. This was Gerard 't Hooft's original insight. This was what Susskind formalized. And this is what Maldacena proved in a specific mathematical context when he showed that a theory of gravity in the interior of a space is exactly equivalent to a theory without gravity on the boundary. But here is where it gets stranger still. In the years after Maldacena's breakthrough, physicists began to explore what the AD-CFT correspondence really meant. They began to ask not just whether the duality was true, but how it worked. How does information on the boundary encode the interior? How does the two-dimensional theory know about the three-dimensional geometry? What is the dictionary that translates between the two descriptions? And the answers they found pointed towards something unexpected, something that connected to a completely different area of physics, something that linked the deepest questions about gravity to the deepest questions about information. The key word is entanglement, quantum entanglement, that strange correlation between distant particles, that connection that Einstein called spooky action at a distance, that feature of quantum mechanics where two particles can be correlated in ways that cannot be explained by any local hidden variables, where measuring one particle instantaneously affects what you will find when you measure the other, no matter how far apart they are. In the years after 2006, a series of physicists, including Shinsei Ryu and Tadashi Takayanagi, working in Japan, made a remarkable discovery. They found that in the AD-CFT correspondence, the geometry of the interior space is connected to the entanglement structure of the boundary theory. The amount of entanglement between different regions of the boundary determines the geometry of the bulk. More entanglement in a certain pattern creates more space in the interior. Less entanglement creates less space. The curves and distances of the three-dimensional world are, in a precise mathematical sense, built from the quantum correlations of the two-dimensional theory. Space is not fundamental. Entanglement is fundamental. Space emerges from entanglement the way temperature emerges from the motion of molecules, the way pressure emerges from the collisions of atoms. Space is not the stage on which physics happens. Space is a consequence of physics, a derived quantity, an emergent phenomenon. This is the Ryuta-Kayanagi formula. It relates the entanglement entropy of a region of the boundary theory to the area of a minimal surface in the bulk, a surface that dips into the extra dimension and captures how much the boundary region is correlated with everything else. The formula is beautiful. The formula is precise. And the formula suggests that everything we thought we knew about the geometry of the universe might be a description of something deeper. Let that thought rest with you for a moment. The space you move through, the distances you travel, the volume of the room you sit in, all of it, according to this picture, is a manifestation of quantum entanglement. The universe holds together not because space is a pre-existing container, but because quantum correlations weave a fabric that we perceive as geometry. Cut the entanglement and you cut the space. Change the pattern of correlations and you change the shape of the world. This is not proven for our universe. The mathematics only works precisely in the AD-CFT setting, in a universe with negative curvature and a boundary at infinity. Our universe is not like that. Our universe is expanding. Our universe has positive curvature at large scales, dark energy pushing things apart, a future that looks more like de Sitter space than anti-de Sitter space. The holographic principle should still apply, but the exact mathematical framework is not yet known. We have pieces of the puzzle, we do not have the complete picture, but the direction of travel is clear. The ideas are too powerful to be confined to a single mathematical example. If entanglement builds geometry in one setting, it probably builds geometry everywhere. If information on boundaries encodes information in bulks in one universe, it probably does so in all universes. The holographic principle is not a curiosity of anti-de Sitter space. It is a hint about the deep structure of reality. And this is where ER equals EPR comes in. Remember, Susskind and Maldacena proposed in 2013 that wormholes and entanglement might be the same thing. An Einstein-Rosen bridge connecting two black holes might be physically identical to Einstein-Podolsky-Rosen entanglement, correlating two quantum systems. The geometry and the quantum mechanics might be two descriptions of one underlying reality. If this is true, then the connection between entanglement and space-time is even tighter than the Ryuta-Kayanagi formula suggests. Not only does entanglement determine the overall shape of space, entanglement literally is the connective tissue of space. Every quantum correlation is a tiny wormhole, a microscopic bridge, a thread linking one point to another. The smoothness of space, the continuity of geometry, the fact that you can move continuously from one location to another, all of this emerges from a vast web of quantum entanglement, an incomprehensibly complex network of correlations knitting reality together. Imagine it this way. Picture the quantum vacuum, the lowest energy state of all the fields in the universe. It is not empty. It is seething with entanglement. Every point is correlated with every other point. Every quantum fluctuation at one location is mirrored, in a statistical sense, by fluctuations everywhere else. And these correlations, these invisible threads, these ghostly connections, they are what make space continuous. They are what allow geometry to exist. Without them, space would fragment. It would dissolve into disconnected points, a dust of locations with no relation to each other. This is speculative. This is not established physics, but it is the direction that many theorists are exploring. It is the shape that the landscape is taking, and it is wild. Wilder, perhaps, than anything Susskind or Hawking imagined when they began their argument in the 1980s. We started with a question about black holes, a question about whether information is destroyed or preserved, and we have ended up questioning the nature of space itself. The war between two physicists has become a rethinking of reality. The puzzle of black hole entropy has become a window into the deeper structure of existence. This is how physics works. You pull on a thread, and the whole tapestry unravels. You ask a simple question, and you end up rebuilding the universe. But there is still more to the story, because all of this, the holographic principle, the emergent space-time, the entanglement-building geometry, all of it raises a question that Hawking in particular spent decades asking, a question that remains, even now, incompletely answered. What happens inside a black hole? Not at the horizon, not on the boundary, inside, in the interior, in the region beyond the point of no return, where the curvature grows without limit. where classical physics predicts a singularity, where all our equations break down. If space-time emerges from entanglement, what does that mean for the singularity? If the holographic principle says that all information is encoded on the boundary, what is the interior even for? Is it real in the same sense that the boundary is real? Is it fundamental, or is it derived? Does it exist at all? Or is it some kind of shadow, a projection, a consequence of a deeper reality that does not require an interior at all? These questions are not resolved. They may not be resolved for a very long time. The mathematics of quantum gravity is hard. The physics of singularities is unknown. The relationship between the holographic description and the interior description is still being worked out. But the questions are no longer mysterious. They are no longer untouchable. They are research programs. They are calculations being done. They are the work of the next generation, building on the foundations that Susskind and Hawking and Maldacena and all the others laid down. Let me try once more to give you a feel for where we are. Imagine you are standing at the edge of a vast ocean. The surface stretches to the horizon. Waves rise and fall. Currents flow beneath. The water seems continuous, smooth, a single substance filling an enormous volume. But you know, if you think about it, that the water is not continuous. It is made of molecules, trillions upon trillions of tiny particles bouncing off each other, attracting and repelling, forming temporary bonds and breaking them. The smoothness is an approximation. The continuity is an emergent property. At the deepest level, there is no water, only molecules, and the properties of water, its density, its temperature, its currents, emerge from the collective behavior of those molecules, from their statistical patterns, from their average motions. Space might be like that. The smoothness of space, the continuity of geometry, the fact that you can draw straight lines and measure distances and watch objects move along trajectories, all of it might be an approximation. At the deepest level, there might be no space, only quantum information, only entanglement, only correlations between abstract degrees of freedom that we do not yet fully understand. And space emerges from those correlations the way water emerges from molecules. It is real, profoundly real as anything you have ever touched or measured. But it is not fundamental, it is derived. It is a pattern in something deeper. This is the vision that has emerged from the war between Susskind and Hawking. Not as a final answer, but as a direction, as a possibility, as a framework that might someday lead to a complete theory of quantum gravity, a theory that explains not just black holes, but the Big Bang, not just horizons, but cosmology, not just the physics of extreme curvature, but the everyday geometry of the world we live in. We are not there yet. We are still in the middle of the journey. The conversation continues, but the shape of the conversation has changed. The questions have evolved. The tools are sharper. The intuitions are deeper. And the strangest idea of all, the idea that started as a wild speculation in the 1990s, has become the foundation of an entire field. The universe is a hologram, or at least it has the information structure of one. The depth is real, the distances are real, the volume is real, but the information lives on boundaries. The 3 dimensions emerge from 2. The bulk is encoded on the surface, and the glue that holds it all together, the thread that weaves the fabric, is quantum entanglement. Rest with that thought for a while. Let it sink in slowly. It does not need to be understood all at once. It does not need to be believed immediately. It is a picture, a possibility, a direction. And like all the deepest ideas in physics, it takes time to absorb. It takes repetition. It takes approaching from different angles, each time seeing a little more. The war is not over. The questions are not answered, but the landscape is clearer than it was. The terrain has been mapped, at least in outline, and the explorers, Susskind, Hawking, Maldacena, and the hundreds of others who followed, have left markers for those who come after. There is one more twist to the story. One more development that emerged in the years after the firewall paradox. One more idea that takes everything we have discussed and pushes it even further. It has to do with islands, not islands of land in an ocean. Islands of information in a sea of radiation. Islands that appear in the mathematics of black hole evaporation. Islands that suggest a resolution to the paradox that started the war. The island formula. The island conjecture. The breakthrough that came in 2019 and the years that followed. A calculation that showed, for for the first time, how information might be preserved during Hawking radiation. A demonstration that the holographic principle, properly applied, really does allow a black hole to evaporate without destroying information. This is where the story turns next. This is where decades of debate found, if not a final answer, at least a promising path. This is where the theoretical physics community began to believe, cautiously, carefully, that Susskind might have been right all along. But that chapter belongs to a later part of our journey. For now, let the ocean of entanglement settle. Let the holographic surface shimmer in your mind. Let the strange architecture of reality, built from information on boundaries and correlations across vast distances, become familiar enough that you can carry it with you into sleep. The fire still burns far away in an isolation that defies imagination. The darkness still stretches, patient and cold, and the question still echoes. The question that Hawking and Susskind argued over for 2 decades. The question that drove them both to the limits of their understanding. Is information preserved? Is the universe coherent? Does physics make sense all the way down? The answer, slowly, is coming into focus. But we are not there yet. We are still gathering the pieces. We are still learning to see. The islands appeared in the mathematics before anyone quite knew what to call them. They emerged from calculations that were, at first, attempts to check old results with new methods, to verify once more whether Hawking's original computation held up when examined through the lens of holography. What the physicists found was not a confirmation. It was something stranger. Something that suggested the geometry of a black hole is not what it appears to be. Something that hinted at regions of space-time that belong informationally to places they seem utterly disconnected from. Picture, one more time, a black hole evaporating. Hawking radiation streaming outward, photon by photon, into the surrounding universe. The black hole shrinking, its horizon contracting, its mass diminishing over eons that stretch beyond comprehension. In Hawking's original picture, each quantum of radiation carries almost no information about the interior. The correlations are weak. The entanglement is local, between partners created at the horizon and then separated, one falling in, one escaping out. The radiation that reaches a distant observer is thermal, random, essentially noise. And when the black hole finally vanishes, whatever fell in is gone. The information is erased. The story ends in silence. But there was always a problem with this picture. Not just the information paradox itself, but a technical problem hidden in the details. A problem that becomes visible when you try to compute something called the entanglement entropy of the radiation. Entanglement entropy is a measure of how correlated two systems are. If you have a quantum system and you divide it into 2 parts, the entanglement entropy tells you how much information is shared between those parts. How much knowing about one part tells you about the other. For a pure quantum state, a state that started with a definite, well-defined wave function, the entanglement entropy between any 2 complementary parts should eventually go back to 0. Because if the whole system is pure, and you collect all the pieces, there are no hidden correlations left. Everything is accounted for. A black hole that forms from a pure state should, if quantum mechanics is correct, evaporate into radiation that is also ultimately pure. The entanglement entropy of the radiation, measured against the remaining black hole, should rise at first, as radiation streams out and becomes entangled with the shrinking interior, and then fall again as the evaporation completes. The curve should go up and then come back down. This is called the Page curve, after the physicist Don Page, who proposed it in 1993. It is the signature of unitary evolution, the fingerprint of information conservation. Hawking's calculation gives a different curve. In his picture, the entanglement entropy just keeps rising. It never comes back down. Because the radiation is thermal, because each photon is uncorrelated with the others, the entropy grows and grows until the black hole vanishes, and then the entropy stays high. The final state is maximally mixed. The information is lost. For decades, the challenge was to show that the Page curve could be derived from first principles, to demonstrate using the mathematics of quantum gravity or string theory or holography that a black hole really does evaporate in a way that preserves information, that the curve really does turn around, that the entropy really does decrease. This is where the islands come in. In 2019, a group of physicists, building on work by Ahmed Almheri, Netta Engelhardt, Donald Marolf, and Henry Maxfield, and in parallel by Jeff Pennington, published a calculation that changed the conversation. They were working within a specific toy model, a two-dimensional version of gravity coupled to a quantum field theory, a simplified setup designed to be tractable, to allow exact computations. Not the real four-dimensional universe, but a laboratory where ideas could be tested. What they found was that when you properly account for quantum corrections to the geometry, when you include the effects of entanglement in the gravitational equations, new regions of spacetime become relevant. Regions that are geometrically inside the black hole, behind the horizon, in the interior, but that are informationally connected to the radiation outside. These regions are the islands. The name is evocative and deliberate. Imagine the radiation as an ocean spreading outward from the black hole. In Hawking's picture, the ocean is all there is. The radiation carries its entropy, its thermal randomness, and nothing from the interior matters. But in the island calculation, there are portions of the interior, islands, that belong, for the purposes of information, to the radiation. They are enclosed by the radiation's entanglement wedge. They are part of the radiation's quantum description, even though they are geometrically separate. Let that sink in for a moment. A region of space-time inside a black hole, behind the event horizon, can be encoded in the radiation outside. Not because anything physically travels from one to the other, not because signals cross the horizon, but because the quantum correlations, the entanglement structure, extends in ways that do not respect the classical geometry. The boundary of what you control informationally is not the same as the boundary you see in space. This is holography taken to its extreme. The idea that information lives on boundaries, that the bulk can be reconstructed from the surface, now applied to black hole evaporation itself. The radiation is the boundary. The island is part of the bulk that the radiation encodes. And when you include the island in your calculation of the entanglement entropy, the numbers change dramatically. They give you the page curve. The entropy rises at first, just as Hawking predicted. The early radiation is entangled with the black hole and the entropy grows. But at a certain point, roughly when the black hole has radiated half its initial entropy, the island contribution kicks in. The island appears in the interior, and it belongs to the radiation. When you compute the entropy including the island, the answer starts to decrease. The curve turns over, the entropy comes back down, and when the black hole has fully evaporated, the final entropy is zero. The radiation is pure, the information is preserved. Say that slowly. Let the weight of it settle. For the first time, using a controlled calculation in a well-defined model, physicists derived the page curve from a gravitational theory. They showed that a black hole can evaporate unitarily. That information is not lost. That Hawking's paradox, the war that raged for 20 years and more, has a resolution in the mathematics of quantum gravity. The island formula is not a proof that the real universe works this way. The model is two-dimensional, simplified, a toy, but it is a proof of concept, a demonstration that the holographic principle, properly applied, can do what Susskind and others always hoped it would do. It can save information. It can make black holes consistent with quantum mechanics. It can turn the paradox into a puzzle with an answer. And the answer involves islands, regions of the interior that sneak into the external description. Pieces of the bulk that are encoded unexpectedly on the boundary. Geometry that lies, or at least geometry that tells only part of the truth. Rest with that thought for a while. The black hole is still there in your imagination, still burning cold against the dark. But now its interior is not quite what it seemed. Parts of it belong to the radiation. Parts of it are already outside, encoded in correlations that stretch across the event horizon. The boundary between inside and outside is not sharp. It is smeared by entanglement. It is complicated by quantum effects. It is an island in an ocean of information. The physicists who developed this picture did not claim to have solved everything. There are still questions, deep questions. The model is two-dimensional. Extending it to 4 dimensions to the real universe remains a challenge. The island formula tells you that information is preserved, but it does not tell you, in detail, how the information comes out. It does not tell you what the experience of an infalling observer would be. It does not resolve the firewall paradox completely, though it points toward a resolution. It gives you the outline of an answer, not the answer itself. But the outline is remarkable. It suggests that the geometry we see, the distances we measure, the horizons we compute, are not the fundamental reality. They are emergent. They are approximate. They are the low-resolution picture that arises when you ignore the quantum correlations, the entanglement, the island effects. The true structure is deeper. The true degrees of freedom are different, and the information, the physical information that tells the universe how to evolve, lives in places we did not expect. This is where Susskind's long journey finds its vindication. Not a complete vindication, physics is never complete, but a strong indication that the direction was right. The holographic principle, complementarity, the idea that information is preserved, that the universe is coherent, that quantum mechanics does not break down at black hole horizons. All of these intuitions, fought for over decades, are supported by the island calculations. Hawking, by the time the island results emerged, had been gone for just over a year. He died in March of 2018, at the age of 76. He did not see the Page curve derived from gravitational calculations. He did not see the island formula. But in his final years, he had already begun to shift. He had conceded in 2004 that information is probably not lost. He had paid off a bet with John Preskill, a bottle of encyclopedias, acknowledging that black holes must preserve information somehow. The mechanism was still unclear, but the direction was set. Information wins. Unitarity holds. The universe does not forget. Let that be a kind of peace, not between theories, but between people. Two giants who argued for 2 decades, who pushed each other to go further, to think deeper, to question assumptions, and in the end, though they never quite agreed, though the details remained contentious, the shape of the answer began to emerge. It emerged from holography. It emerged from entanglement. It emerged from the strange mathematics of boundaries and bulks, of information encoded on surfaces, of geometry that is not fundamental but constructed. The war is not over. Physics does not end with a victory parade. There are still researchers who question the holographic principle. There are still debates about the firewall paradox. There are still attempts to find alternatives, to test the ideas, to push them to their limits. But the centre of gravity has shifted. The consensus, if there is such a thing in theoretical physics, has moved towards Susskind's camp. Information is preserved. Black holes are consistent with quantum mechanics. The universe is a hologram, or something very much like one, and the islands are part of the map. Think about what this means for the nature of space, for the geometry of the world. If islands are real, if regions of the interior can be encoded in the exterior, if the entanglement structure can override the classical distances, then space is not what we thought it was. It is not a fixed stage on which physics plays out. It is not a container for particles and fields. It is emergent. It is flexible. It is woven from something more fundamental, something that has to do with quantum information, with correlations, with the way systems are entangled across vast distances. The distance from your eye to the stars is real. The light takes time to cross it. The photons travel at a fixed speed, and the journey is long. But the information that tells the universe how those photons behave, the correlations that connect your observation to the source, those might live on a boundary, encoded in a way that does not respect the geometry you see. The 3 dimensions of your experience might emerge from a 2-dimensional structure that is more fundamental. The depth might be a construct, a projection, a hologram. This is not mysticism. It is not metaphor. It is the direction that the mathematics points. It is the lesson of add CFT, of complementarity, of the island formula. It is the picture that emerged from the war over information, the war that Hawking and Susskind fought, the war that reshaped our understanding of black holes and gravity and the quantum nature of space-time. Let it sit. Let it become familiar. It does not need to be believed immediately. It does not need to be understood all at once. It is a picture, a possibility, a direction. And like all the deepest ideas in physics, it takes time to absorb. The black hole still burns, out there in your imagination. The radiation still streams away, carrying its subtle correlations. The islands still hide in the interior, waiting to be included in the calculation. And the question still echoes, the question that drove 2 decades of argument and insight and breakthrough. Is the universe coherent? Does physics make sense all the way down? The answer, slowly, is coming into focus. But there is one more piece to consider, one more implication that the island formula and the holographic principle suggest. Something that goes beyond black holes, beyond horizons, beyond the specific puzzles that Hawking and Susskind fought over. something that touches the nature of reality itself. It has to do with observers, with what it means to be inside versus outside, with the limits of what any single perspective can know. In classical physics, space is shared. Everyone agrees on what exists, where it exists, when it exists. The geometry is universal. The facts are objective. There is one world, and all observers see the same one, just from different angles. But in quantum mechanics, observation is more complex. Measurement affects the system. Outcomes are probabilistic. And in quantum gravity, in the holographic picture, the very geometry of space-time depends on which boundary you use to describe it. Depends on which system you call the exterior and which you call the interior. Depends on where you stand. The island formula shows that an observer outside a black hole can reconstruct parts of the interior. The radiation encodes the island. The correlations span the horizon. But this does not mean that the interior is accessible in any physical sense. An observer who falls in still crosses the horizon, still encounters whatever waits inside, still has experiences that are hidden from the outside. The two descriptions, inside and outside, are complementary. They are both valid, but they are not the same. This is complementarity again, the idea that Susskind proposed in the 1990s, the idea that seemed radical at the time, that troubled so many physicists, that led to firewalls and paradoxes and decades of debate. The island formula does not eliminate complementarity, it deepens it. It shows that the complementary descriptions are connected by entanglement, by information, by the quantum structure of spacetime itself. And this leads to a strange and unsettling possibility, that there is no single, objective, universal description of reality, that the geometry you see depends on the questions you ask, that the space you inhabit is constructed from the information available to you, that different observers, in different situations, live in different geometries, all equally valid, all mutually consistent when properly translated, but none of them the whole truth. This is not solipsism, it is not relativism, it is something subtler. It is the recognition that in a quantum universe, in a holographic universe, the act of observation is not passive. It is constitutive. The observer is part of the system, the boundary is part of the bulk, and the story cannot be told from a God's eye view, because there is no God's eye. There is only the web of correlations, the pattern of entanglement, the information encoded on whichever boundary you choose to call your own. Rest with that thought gently. It does not need to be alarming. It is not a threat. It is a deepening of the mystery, a recognition that the universe is stranger than the classical picture suggested, that the solid ground of objective space and time is perhaps a construction, a convenient illusion, a low-resolution approximation to something more intricate, more quantum, more entangled. The black hole teaches this lesson. The horizon, that boundary between inside and outside, is not as sharp as it seemed. The information is not lost, it is transformed. The geometry is not fixed, it is emergent. And the observer is not separate from the system. The observer is woven into it, entangled with it, part of the holographic fabric. This is what the war was about in the end. Not just information, not just black holes, not just the fate of a photon that falls past an event horizon. It was about the nature of reality, about whether the universe is fundamentally classical or fundamentally quantum, about whether space and time are the bedrock or the surface, about whether the laws of physics hold everywhere at all scales in all circumstances, or whether they need to be replaced, reinterpreted, reimagined. Susskind believed they hold. Hawking believed they need modification. And the island formula, emerging decades after their debate began, suggests that Susskind's instinct was correct, but that holding on to quantum mechanics requires giving up on classical geometry, requires accepting that space is emergent, requires embracing the holographic principle, not as a curiosity of string theory, but as a fundamental feature of nature. The universe is a hologram. The information lives on the boundary. The entanglement weaves the fabric of space. And the islands, those unexpected regions of the interior that belong to the exterior, are part of the map that is still being drawn. Let the ocean settle. Let the islands rest. Quiet in the mathematics. Let the distant black hole shimmer, ancient and patient, burning without consuming. The fire still glows against the darkness. The questions still echo in the silence, and the answer, slowly, is coming into focus. But we are still learning. We are still gathering the pieces. We are still, all of us, finding our way through the strange geometry of a universe that encodes its secrets on surfaces, that hides its depth in dimensions we cannot see, that preserves its information in patterns of entanglement stretching across the void. The war is not over. The story is not finished. But the landscape is clearer than it was. The terrain has been mapped, at least in outline, and the markers left by Susskind and Hawking and the generations who followed light the path for those who come after. Somewhere in the mathematics the islands wait. Somewhere in the correlations the information is preserved, and somewhere in the patient dark the universe keeps its coherence. Not because we understand it, but because it was coherent all along. We are just learning to see. We are just learning to see. And perhaps that is the most honest way to describe where we are now in this slow unfolding of understanding. The war that began in a conference room in San Francisco, that continued through papers and counterpapers, through lectures and debates, through decades of calculation and argument, has reached something like a resolution. Not a final answer, not a complete theory, but a clearing in the forest, a place where the path becomes visible, where the shape of things begins to emerge from the fog. Susskind is still alive as these words are written, still thinking, still working, still giving lectures to students who were not born when the debate began. And when he speaks about Hawking now, there is something in his voice that goes beyond intellectual respect. There is the particular warmth reserved for a worthy opponent, a fellow traveller on a difficult road, a mind that pushed his own mind to places it would never have gone alone. Hawking died in March of 2018, the same month, almost to the day, that he was born 76 years earlier. He had lived more than 5 decades past his initial diagnosis. He had watched his children grow up, had seen his grandchildren born, had travelled the world in a wheelchair that became as iconic as any spacecraft. And he had changed his mind. That is worth dwelling on, worth letting it settle into the bones of this story. Stephen Hawking, one of the most celebrated physicists of his generation, a man whose popular books shaped how millions of people think about the universe, a scientist whose name became synonymous with brilliant certainty, changed his mind. Not quietly, not reluctantly, but publicly, graciously, with the kind of intellectual honesty that is rarer than genius. At a conference in Dublin in 2004, 30 years after the bet was placed, Hawking conceded. He presented a new calculation, a new approach to the black hole information problem, and acknowledged that Susskind and Tufte had been right. Information is not destroyed. Quantum mechanics holds. The laws of physics remain unbroken. He gave Preskill an encyclopedia. That was the original wager, an encyclopedia in which, as Hawking had put it, the winner could find information at will. Preskill accepted it with a smile. Thorne, the third party to the bet, was more cautious. He said he wasn't ready to concede yet. The details were still unclear. The mechanism was still murky, and in some ways Thorne was right to hesitate. Because even now, even with the page curve resolved and the island formula in hand, the story is not complete. We still do not know, in any visceral or picturable sense, how the information gets out. We have the mathematics, we have the entanglement entropy calculations, we have the consistency arguments, but we do not have the movie. We cannot watch a bit of information fall into a black hole and trace its journey back out. The mechanism remains hidden behind the curtain of Planck-scale physics, of quantum gravity, of a theory we do not yet possess. But the outline is there, the shape is clear, and the shape vindicates Susskind's deepest intuition. Think about what that means. A 30-year argument, a public bet. 2 of the most formidable minds in theoretical physics, grinding against each other decade after decade, neither willing to yield, neither able to convince the other with the tools available at the time. And in the end, the universe sided with one of them. Not because Susskind was smarter, not because Hawking was careless, but because the universe has a structure, and that structure, encoded in the mathematics of quantum gravity, preserves information. The holographic principle is not a speculation, it is not a philosophy, it is a feature of how reality works, at least in the corners of physics where we can check. The war is over, Susskind won. But say it gently, because the winning and losing here is not the point. The point is what the war revealed, what the struggle uncovered, what the decades of argument forced both sides to discover. Before the black hole information paradox, physicists thought they understood space. They thought they understood time. They thought quantum mechanics and general relativity were both correct, just applicable to different scales, and that someday a clever enough theorist would find a way to glue them together. The paradox shattered that complacency. It showed that the gluing is not simple, that something has to give, that the smooth classical geometry of space-time cannot be the final word, and the resolution, the holographic resolution, the entanglement resolution, the island resolution, points towards something stranger than anyone expected. Space is not fundamental. It is woven from information. It is knit together from correlations, from entanglement, from the quantum threads that connect distant parts of the universe in ways that have no classical analogue. This is what Susskind glimpsed all those years ago when he first heard Hawking's claim and felt the wrongness of it in his bones. He did not know then that the answer would involve holography. He did not know about complementarity or firewalls or islands. He knew only that information could not be destroyed, that quantum mechanics could not be violated, that there had to be a way out. And there was. There is. The universe found it, or rather, the universe always had it, and the physicists, Susskind and Hawking and Maldacena, and Hooft and Page and Pennington and all the others, slowly, painstakingly over decades learned to see it. Now turn for a moment from the physics to the people, because this story is not just about equations, it is about two human beings, wrestling with the deepest questions, pushing against each other and against the unknown, trying to see something that no one had seen before. Susskind, the former plumber from the South Bronx, who came to physics late and came to it hungry, who taught himself the mathematics of curved space and quantum fields, who fought his way into the elite world of theoretical physics without the pedigree, without the connections, without the polish, who never lost the edge, the combativeness, the unwillingness to accept authority on faith. When he heard Hawking say that information is destroyed, he did not bow to Hawking's reputation. He did not defer to the consensus. He went to war, and Hawking, the English prodigy, who was given 2 years to live at 21 and lived for 50 more, who built a career from a wheelchair, who wrote equations without the use of his hands, who lectured without the use of his voice, who became the most famous scientist in the world, a symbol of the triumph of mind over matter, and who, despite the fame, despite the honours, despite the temptation to rest on his achievements, kept working, kept thinking, kept pushing, kept arguing with Susskind long after he could have declared victory and walked away. They needed each other. That is the strange truth at the heart of this story. Without Hawking's paradox, Susskind would never have discovered complementarity. Without Susskind's resistance, Hawking might never have reconsidered his position. The war was productive, the conflict was generative. The decades of disagreement forged something that neither of them could have made alone. This is how science works, when it works well. Not through peaceful consensus, not through quiet agreement, but through argument, through challenge, through the willingness to stand in front of a room and say, "You are wrong," and then to spend 30 years proving it, or being proven wrong yourself and having the grace to admit it. Hawking had that grace. When he conceded in Dublin, he did not hedge. He did not qualify. He did not say, "I might have been wrong, but the jury is still out." He said information is preserved. He said Susskind was right. He said the laws of physics hold, and then he went back to work. Because the concession was not an ending, it was a clearing, a place to begin again, with the landscape better mapped, with the question rephrased, with the mystery deepened rather than solved. Let that settle. Let the weight of it rest in the quiet. Two physicists went to war for 20 years over whether the universe is a hologram. One believed that black holes destroy information, that quantum mechanics breaks down at the event horizon, that the deepest secrets of the cosmos are lost forever when matter crosses that one-way boundary. The other believed that information is eternal, that the laws of physics are inviolable, that somehow, through some mechanism not yet understood, the story is preserved. Only one could be right. And the one who was right, the one whose instinct was vindicated, whose stubbornness was rewarded, whose decades of argument proved prescient, that physicist discovered something more surprising than he expected. The answer was not a minor adjustment. It was not a patch. It was a revolution. The universe is a hologram. Space is emergent. Information is fundamental. And the beautiful, intuitive, comforting picture of reality, the one where space is a stage and matter is the actor, is an approximation, a useful fiction, a low-resolution rendering of something deeper. The holographic principle is strange, it is counterintuitive, it is difficult to picture and impossible to feel. We walk through three-dimensional space. We reach out and touch three-dimensional objects. We live our lives in a world that feels solid, volumetric, deep. And yet the mathematics says that everything we experience, every thought and sensation and memory, every star and planet and person, could in principle be encoded on a two-dimensional surface. That the interior is not additional to the boundary. That the boundary is enough. This is not a metaphor. It is not poetry dressed in equations. It is a statement about the maximum information content of a region of space, derived from the thermodynamics of black holes, confirmed in the mathematics of string theory, woven into the resolution of the information paradox. The universe does not have to be a hologram, but it is. Why? We do not know. That is the honest answer. The holographic principle follows from calculations we trust, calculations that have been checked and rechecked and found consistent. But we do not have a deep understanding of why the principle holds. We do not know what it is about the fundamental structure of reality that makes the boundary sufficient, that makes the bulk emergent, that makes information the bedrock and space the construction. Someday, perhaps, we will know. Someday there may be a theory of quantum gravity that explains not just that the holographic principle is true, but why it had to be true. That theory does not exist yet. String theory is a candidate. Loop quantum gravity is another. There are ideas and approaches and partial results scattered across the landscape of theoretical physics like stones waiting to be assembled into a wall. But the wall is not built. The theory is not complete. And so we wait. We calculate. We argue. We push against the unknown, as Susskind and Hawking pushed against each other, as physicists have always pushed against the darkness at the edge of knowledge. The fire still burns, the questions still echo, and the universe, patient and strange, keeps its secrets on surfaces we are only beginning to read. Rest now, if you like. Let the mathematics settle into something quieter. Let the black holes fade into the background hum of the cosmos, those ancient objects with their impossible horizons and their coded memories. Let the hologram shimmer, not as a thing to be grasped, but as a reminder that the world is stranger than it appears, that depth is not what it seems, that the act of observation is woven into the fabric of what is observed. Susskind, in his later years, has spoken often about what the Black Hole War taught him, not just about physics, about the nature of scientific understanding itself. He has said that the universe is not obligated to make sense to us, that our intuitions, evolved for a world of rocks and trees and predators, are not calibrated for the quantum realm, for the relativistic realm, for the holographic realm, and yet somehow against all odds the mathematics works. The equations describe, the predictions come true. This is the miracle, if we want to call it that. Not that the universe is strange, of course it is strange, but that we can understand it at all. That creatures made of atoms living on a small planet orbiting an ordinary star can scratch symbols on paper and touch the edges of cosmic truth. That the same quantum mechanics that governs electrons in a circuit governs the information content of black holes. That the same general relativity that bends starlight around the sun describes the event horizons of objects billions of light years away. The laws of physics hold. They hold everywhere we have checked. They hold at scales we can barely imagine. They hold in the interiors of neutron stars and in the roiling plasma of the early universe, and at the edges of black holes where space and time twist into geometries that have no name. Susskind was right to trust them. Hawking was right to test them. And the testing, the questioning, the relentless pressure of paradox and argument led us here, to a place where the laws are stranger than we thought, but still unbroken. The universe is a hologram. The information is preserved. The islands wait in the mathematics. And the story, the long story of matter and energy and space and time, continues to write itself on the boundaries of existence. Close your eyes, if you like. The darkness is not empty. It is full of information, encoded in patterns we're only beginning to understand. The distant stars are campfires in that darkness, each one a temporary arrangement of matter, a local concentration of order, a brief bright defiance of entropy. And the black holes scattered among them, the ancient ones, the patient ones, the keepers of secrets, are not destroyers. They are transformers. They take what falls into them and write it on their horizons in letters too small to read, in a language we are still learning to speak. Hawking found the letters. Susskind insisted they were there, and the generations that followed, Maldacena with his correspondence, Page with his curve, Pennington and the others with their islands, they are reading them, slowly, painstakingly, one equation at a time. The war is over, but the story is not finished. It never is in science. Every answer opens new questions. Every clearing reveals new forests beyond. The holographic principle is established, but we do not know why it is true. The information paradox is resolved, but we do not know what happens to an observer who falls into a black hole. The Page curve is calculated, but we do not know what the microscopic mechanism looks like in full quantum gravity. These are not failures, they are invitations. They are the questions that will occupy the next generation, and the generation after that, and perhaps generations we cannot imagine. Somewhere, right now, a student is learning quantum mechanics for the first time, sitting in a lecture hall or hunched over a textbook in a library or watching videos on a glowing screen in the dark. They do not know yet where the equations will take them. They do not know about black holes or holography or the war that raged for decades in the pages of journals and the corridors of conferences. They know only that the mathematics is beautiful, that the questions are deep, that something about the structure of reality calls to them in a way they cannot explain. That student may be the one who takes the next step, who sees what Susskind and Hawking could not see, who finds the deeper theory, the unifying principle, the explanation that turns the holographic principle from a result into an inevitability. Or they may not. They may work their whole career and make only incremental progress, small steps in a long journey. That is how science usually works. Not in leaps, but in footsteps. Not in revelations, but in the slow accumulation of evidence, the gradual refinement of understanding, the patient building of a picture that will never be complete. Either way, the work continues, the fire burns, the questions echo, and the universe, encoded on its surfaces, waits to be read. Let that be enough for now. Let the story rest in this clearing, with the trees all around and the sky visible above, the stars scattered across the darkness like messages in an unknown script. Two physicists went to war. One insisted that the laws of physics could break. The other insisted they could not. For 20 years they argued, calculated, pushed against each other and against the limits of human understanding. Only one could be right, and the one who was right discovered something neither of them expected at the start. That being right meant embracing a universe stranger than either had imagined, that the victory came not through defending the familiar, but through following the equations into unfamiliar territory. That the information is preserved, yes, but preserved in a way that dissolves the very notion of interior and exterior, that makes space itself an emergent phenomenon, that writes the secrets of the cosmos on surfaces we cannot touch. The universe is a hologram. The boundary holds the story. The bulk is a reading. And we, all of us, with our three-dimensional bodies and our three-dimensional intuitions, we are part of that reading. Patterns in the code, ripples in the information. Thoughts thinking themselves in a hologram that does not know it is a hologram, because there is no outside from which to see. This is not a diminishment. It is not a reduction. It is a deepening. A recognition that the universe is richer than appearances suggest, more unified than our categories allow, more quantum than our evolved intuitions can easily accept. Hawking taught us that black holes are not silent. Susskind taught us that their whispers are not lost. And together, across decades of argument and discovery, they opened a door that will never close. The fire still glows against the darkness. The questions still echo in the mathematics. And somewhere, in the patient geometry of existence, the information is preserved, waiting, as it always was, to be understood. We are still learning to see, but we are learning.